Okay, good morning. Welcome to our class, Engineering Mechanics 2. Right now we are in Chapter 5. We started discussing the theory of Chapter 5 in our last class, and this concerns how to compute the characteristic values of mass moment of inertia. And today we will have a look at several exercises and on how to derive this mass moment of inertia. Let's have a look at our script. There it is. And so this is where we stopped the discussion on how to solve, how to compute the mass moment of inertia. And these are our Chapter 5 exercises. Sorry, seems to be a bit slow today. Here it is. And this is our first exercise, exercise 5.1. with which we will start today. What do we have? We have a box given with the dimensions A, B, and C. A has gone missing. There it is. And we have to find the mass moment of inertia with respect to the depicted center line for a rotation with omega A in the first part, and in the second part we have to find the mass moment of inertia for the depicted edge of the body, rotation with omega B. So for the first case, oh sorry, it was still open. Okay. First of all, we have to decide which are our main axis of the system. The main axis, no, the center of the main axis is in the center of gravity of our object, which is the start right here. And then we have x-axis, y-axis, and z-axis according to the direction of our box, parallel to length A, to B, and to C. X, Y, and Z. Now, in case A, we want to consider the rotation about the center of gravity, about the axis, about the x-axis. Okay, and the x-axis is our main axis of the system. Now, the general equation to obtain the mass moment of inertia, Jx, in case A, situation A, is the following. It's the square of the radius in x direction integrated over the mass. Now, the radius from our x-axis in general is y square plus z square dm. Maybe easier to understand if we draw a side view of the box like this. This is C, this is B, this is our coordinate system, y-axis and z-axis. Now the radius for any point in the system, small mass element, dm, can be found by computing the radius dependent on the system. For example, there could be a small mass element dm, and the radius of this mass element, distance from our axis of rotation, is this one right here. Now, this is a or we can draw this as a triangle, for example, like this. Now, the green line corresponds to the distance in Z direction and the distance in Y direction. Now, the red line, our radius, R is equal to Y square plus Z square. In general terms, of course, not for the specific mass element, but for an arbitrary mass element in our system. Can be in any other position as well. Here, for example, or wherever. Then we could derive the radius from there. Okay, now we cannot directly integrate over mass, but we have to change into variables that we know that we are able to integrate. So the mass, small mass element dm, can be computed by density multiplied by the volume of the small mass element, dV. And the volume for a cuboid can be derived by length times width times height, like this. Now, if we substitute this into our equation, we obtain y square plus z square times rho times dx dy and dz. Well, we have a triangle with a right angle like this. This is our radius. There's our right angle. This is the distance from the origin, from our x-axis in z direction. In general, it's our value set. And this is the distance from our mass element to the x-axis in y direction. Okay, yeah, exactly. Okay, now this is our integral that we have to solve. And of course, we have to state the boundaries of our integral. Since I do not have enough space in the equation above, I will state it again. Y square plus z square. Rho is constant, so we do not have to integrate over the density, dx, dy, dz. So then we have to start from inside, from the inside, and then move on to the outside when integrating. Our inner integral is the integration over the x coordinate, and x runs from minus minus a over 2 to a over 2, according to our coordinate system that I drew in the figure. Now the y coordinate runs from minus b over 2. Oh, it's minus c over 2 to plus c over 2. And the same for the z coordinate from minus b over 2 to plus b over 2. Okay, now we have to solve this equation. We start with the integration over x, which is simple since integrating over x, the value inside of the integral is a constant. Then we have rho minus b over 2 to b over 2 minus c over 2, c over 2. Then we solve y squared plus z squared times x in the boundary of minus a over 2 dA over 2. The whole length is b. Okay, then if we insert our boundary, then we obtain a, so it's rho times a, and then minus b over 2, b over 2. Okay, and then we can integrate over y, our y coordinate. So rho times a. So for the first one, we have 1/3 y to the power of 3 plus z squared times y in the boundaries of minus c over 2 to c over 2. Now, if we enter our boundaries, then we obtain rho times a minus b over 2 to b over 2. So 1/3 times c half to the power of 3. Then this is 1/12. Plus z squared times y, and this is z squared times c. C half plus c half is c. dz. Okay, so one last integral that we have to solve. And it's rho times a 1/12 c to the power of 3 times z plus c 1/3 z to the power of 3. Then this is rho times a times 1/12 c to the power of 3 times b plus 1/12 c b to the power of 3.
For the boundary conditions, have you written b by 3 or b by 2?
Oh, sorry. Yeah, thank you. Should be a 2. You're right. So now we can rearrange this equation, and we have rho times A, B, C, 1/12, and then there's B squared plus C squared. Now, ABC is the volume of the cuboid, and rho times volume equals the mass. And then this means we have 1/12 mass B squared plus C squared. And that's our mass moment of inertia with respect to the main x-axis. This is how the integration works. General procedure for an arbitrary mass, arbitrary object. But of course, a cuboid is a simple structure, and we could just use the table to find the mass moment of inertia of the system. So let's have a look at the formulary. Here's our cuboid. Now we have to make sure that we insert the right dimensions of our specific system, but in general it's 1/12 times mass, and here height square plus v square, and in our case h is equal to c. Okay, so for these simple structures, these simple geometries, we do not need to integrate the system, but in general, this would be the steps we'd have to take. Now, for the second situation, case B, I will move upward here. We want to compute the mass moment of inertia with respect to this axis right here. Now we assume that the cuboid rotates about this axis with omega b. And our mass moment of the size of our mass moment of inertia depends on the axis of rotation. Now in this case, the axis of rotation is parallelly shifted to our original axis of rotation. And for this, I have a formula as well. On the previous page, it's already marked. So it's this line right here. In case of a parallelly shifted axis from a main axis, we have to include the Steiner share to our mass moment of inertia. Now, if we apply this equation, then we have J x b is equal to J x a plus mass times E squared. This is the Steiner share, and E is the distance from our original axis, from our main axis, to the current axis of rotation. And again, draw it over here, B and C. this is our current axis of rotation, and this is our new axis of rotation. And again, we have to find the distance E, radius from original to current axis of rotation. Then this is 112 m b squared plus c squared, and E squared is b over 2 square plus square of c over 2. Then for the second part, it is 1/4 mass times b squared plus c squared, and 1/12 plus 1/4 is 1/3 m b squared plus c squared. Okay, so that's the last part. If our axis is parallelly shifted from our main axis, as in this figure right here, then we have to consider the Steiner shear. The mass moment of inertia affects the inertial moment of our system, the inertia against the change of motion. And if my object rotates about the center of gravity, then the mass moment of inertia has a specific size as given in our first part of the problem, solution of the first part. And if the axis is shifted, the size of the mass moment of inertia changes. It increases since more mass is further away from the axis of rotation. I need more higher force to change the motion, the kind of motion of the system, if my mass is further away from the axis of rotation. Then the mass moment of inertia increases, and this factor is included or is considered in the Steiner shear. And it's E squared, just E squared. In the formula, it's E squared, but here not. That's the question. Then the Steiner shear consists of mass multiplied by the distance from the axis, from the main axis to the axis of rotation. And again, this is our triangle. This part here is b over 2, and this here is c over 2. Then E is equal to square root of a squared plus b squared. More general triangle like this. And since we have to square the distance, then we can neglect the square root.
Professor, I have a question.
Yes.
How did 1/12m become 1/3m? By what?
This is 1/12,
Yeah.
and this is 1/4.
Okay.
And 1/12 plus 1/4 is 1/3.
Oh, thank you. Thank you.
Yes, I have a question to the diagram. If you could.
Yes.
Yeah, the four symbols or those four things. Could you please explain them?
Which things?
If you go to the diagram of the cuboid.
The original, yeah, okay.
Yeah, and then these four along the length on both sides.
This?
Yeah, these four.
Okay. This is the support. The support of the axis. So it's like in strength of materials, you probably saw this, and or in statics there was an example as well. I think it's like you have a shaft, for example, like this, which is rotating, and then there are supports holding the shaft, usually a bearing or something like that.
Yeah, understood. Understood.
And that's what meant by this diagram.
All right.
Okay.
Thank you.
So they enable the rotation, but no translational motion in vertical direction. Okay. Further questions? Okay, if not, then let's have a look at the second example. Next problem, 5.2. We have a thin circular disc with given density, radius, and width. And it's given that the width is significantly smaller than the radius. And it is mounted tilted. So it's not straight, but it's tilted by an angle delta. And we have to find the mass moment of inertia regarding the rotational axis. Now, let's draw this the system. This is our axis of rotation, and this is the support. I'll just increase this a little bit, and this is our disk. This is the radius. Now, the main axis of the disk is this one. In the center of gravity and parallel to the dimensions length and or width and radius in this case. But the axis, the coordinate system for the axis of rotation is this one right here. This is the coordinate system for the actual motion. The disk rotates about the axis x star. And we have this angle delta between these two axes. Okay. Now, first of all, we have to figure out which are the mass moments of inertia of the main axis of the system. And let's have a look at the formulary. On the bottom here, you can see the equations for the mass moment of inertia when the axes are rotated. So these are the equations we want to use, but we need our original mass moments of inertia in the equation. So we need to go to the next slide and decide which one of these standard objects might be our disk. And the closest object is the first one, the hollow cylinder. In our case, the length of the cylinder here corresponds to the width of our disk. The inner radius doesn't exist in our case because our disk is not hollow. So the small r is equal to 0. And then we can use these two equations for the mass moment of inertia with respect to the x-axis and with respect to the y-axis. Okay, now I will state them for our problem. So again, we use the formula for the hollow cylinder with r equals 0 and L equals to S. Then Jx is equal to 1/2 mr square, and Jy is equal to 1/4 mr square plus 1/3 s square. Now, knowing that the width is significantly smaller than the radius, we can neglect the second part of this equation. Which gives us 1/4 mass, times r square, square of the radius. Okay, and since our axes are the main axis of the system, then Jxy is equal to 0. Okay, then let's apply the equation for the mass moment of inertia with respect to the axis of rotation. Yes.
Why is Jxy equal to 0? What is Jxy?
Because x and y are the main axis of our system. We picked them as our main axis, so that simplified our computation.
But what is Jxy?
Excuse me?
What is Jxy?
That's the centrifugal moment. So if this is our disk, and we would have chosen this coordinate system, for example, as our initial coordinate system, then there would be a Jxy, a centrifugal moment, because then our axis, our x-axis at least, would correspond to the main axis of the system. The main axis always passes through the center of gravity of the system. So if a system like this here would be given, then we would have to compute Jxy.
Okay, thank you.
Mm-hmm. Okay, then the equation from the formulary is as follows. It's 1/2 Jx plus Jy plus 1/2 Jx minus Jy times cosine of 2 delta plus Jxy times sine of 2 delta. Okay, this is 0. And then we can state everything else. 1/2 mass times radius square, 1/2 plus 1/4 plus 1/2 r square, 1/2 minus 1/4 times cosine of 2 delta. Then 1/2 plus 1/4 is 3/4, and 1/2 minus 1/4 is 1/4. Then we have 3/8 r square plus 1/8 mr square cosine of 2 delta. Now the small r is 0 of the hollow cylinder, meaning that there is no hole inside, it's not hollow. Then the disk would look like this. So this is small r, and this is capital R. But in our case, the disk is not hollow. And there's only capital R, and the small r is 0. Okay, we can rearrange this equation a bit more. For example, we could state that we have 1/2 mr squared times 3/4 plus 1/4 cosine of 2 delta. Then this would be equal to the mass moment of inertia with respect to the main axis. Okay, then this is the result of the second question, the second problem. If there are no further questions.
Excuse me, Prof. Concerning that moment of inertia towards xy, that's jxy. If we wanted to give it in a plane or put it in a diagram, how should it be like? Or is it a product? And also, if we want to get it, is it a product of jx times jy that will give us jxy?
No, it's stated in the formula how you can compute this variable. Where's my mouse? Here. So here it says that they are 0 if our coordinate system is positioned in the center of gravity and correspond to our main axis. Our axis correspond to our main axis. And jxy actually doesn't seem to be my mouse. The equation of jxy is not stated here. It's written in our script. Is it here? No. Oh. So that's that would be something for your notes. Just copy it from the script. jxy, for example, would be minus, and then the integral of x times y over dm. So you'd have to integrate this again. Okay. Will look like this. We can maybe we can make a small example computing the centrifugal moment if you like. There's another question. Just this equation right here is stated in the formulary. That's the first line. Rotation of the axis. I just copy it from the formulary. Yeah. Okay. Maybe instead of solving another problem, let's do a small example concerning the centrifugal moment. Okay. This is our coordinate system, and we have an maybe an object like just like this. So this would be the sorry. This coordinate system is not our doesn't correspond to our main axis, since it doesn't pass through the center of gravity. That's why I call it X star and Y star. We have two subsystems, substructures, two cuboids, more or less. Okay, and then let's call this part A1 and this one here A2. And we do know the center of gravity for the individual systems or subsystems, as in engineering mechanics 1, when you had to compute the center of gravity of a general object and you had to break it down to simple structures, circles, triangles, and rectangles. We do the same here. Now, we do know the position of our coordinate system for the main axis. It would be these. Now, to solve this, we need some coordinates, at least for the positions for the center of gravities of our subsystems. I'll just use A and 2A. Now, let's have a look at the formulary again. In our main axis, the centrifugal moment is equal to 0, stated here. And then if we shift the axis of rotation of our centrifugal moment, we also have to consider Steiner's share, E squared times m. And that's what we will do now. We assume that this is our axis of rotation. We rotate about the center of gravity of our given global coordinate system. Then for the first subsystem, J, X, Y, and then I'll write it here for area 1, A1. For our original coordinate system, which is situated in the center of gravity and corresponds to our main axis, the centrifugal moment is equal to 0. But then we shift the centrifugal moment with respect to our axis of rotation. And for the first subsystem, this is E1, this distance right here. I'll state it in general first. It's not a scale drawing. As you can see here, A in X direction corresponds to 3.5 boxes, and in Y direction to 2 boxes. It's not correctly scaled. The X scale is different than the Y scale. I just picked numbers to keep the computation simple. Okay, now let's apply this equation. So it's minus, then in X direction, we have a distance of A, and in Y direction of 2A, and then we have to multiply by the area A1. And the same for the second subsystem. It's A, distance A in X, and distance A in Y direction times A2. And then for the absolute centrifugal moment, the centrifugal moment of the entire system, we simply have to add them. A1, XY, A2. Then we would obtain minus A squared 2A1 plus A2. Not knowing how big the dimension or the area is right now. But this is how it would work. You would also, again, you would start out with your main axis, then you could shift the main axis. For the centrifugal moment, you have to multiply the distance in X and Y direction, and then multiply this by the area itself. And then you sum your subsystems to obtain the global centrifugal moment. But usually in our problems that we will discuss in class, the centrifugal moment is 0. Because we simply pick the main axis as our axis for describing the mass moment of inertia. Okay, then let's have a look at another example. It's problem 5.4. This is not part of the problem. That's from the problem above. Okay. What do we have? We have a flywheel made of cast iron. The answer here is given, and it has 4 drill holes of diameter of 120 millimeter, which are placed evenly over the circumference. We have to find the mass moment of inertia and the radius of gyration regarding the rotational axis. And then it's also asked for the share of the annulus on the mass and the mass moment of inertia. Now this is a drawing of a mechanical system as you would find in or you know from strength of materials, I guess. So it's only the side view, a cut through the flywheel, and we only see the upper half of the system. This is our axis of rotation right here, and you have the diameters given. So it's the lower side is identical to the upper side, the system drawn here. Since it usually causes difficulty understanding how the system, how the flywheel looks like, I will draw the front view of the entire flywheel. Okay, so for this, this is the outer radius of the flywheel. Then this would be the axis of rotation. So that's the first material. And then like this. And we have the 4 drill holes. Like this. And it rotates in this direction. Then this is material. This and this. Okay, and it rotates about its center. This is our axis of rotation. Due to the different thicknesses of these of the flywheel, we have to break it down to different subsystems. So we could number our subsystems. For example, this would be our first subsystem. This part of the flywheel would be the second subsystem. The drill holes would be the third, and this one, the fourth. According to the figure given, this would be the fourth, this would be one of the drill holes. Maybe I use different colors for 2. Then this would be number 2. And this subsystem number 1. One, 2, and 4 are hollow cylinders. All of them rotate about their main axis, about their center of gravity. That's a question? No? Okay. All of them rotate about their center of gravity. And then we have the full cylinders, our drill holes, which we have to subtract from the system since they are drill holes, they do not exist, no materials. These are 4 negative full cylinders. Which rotate about an axis that is parallelly shifted to the main axis of the cylinder. It's rho times L times square of the radius, like this. And the mass moment of inertia of the main axis of a hollow cylinder, in this case, is basically that what we just stated in the previous problem, 1/2 mi r(I) square plus square of the inner radius. This is. Now, as you learn in statics, we can build a table and simply fill the relevant information for every subsystem, and then we can sum over the subsystems to obtain the absolute value. Okay, so we need the number of our subsystem, then we need the radii, outer and inner. I'd recommend to state it in meters right away, then we do not have to worry about the dimensions. That's not a free body diagram that I draw there, because we are not talking about forces or anything like that. We are simply computing the mass moment of inertia. I just draw the free body diagram for you to better understand how the system looks like. The information given in the problem description would be enough to understand how the system looks like and which dimensions, radius, length, etc. we need. Okay, so this this figure right here is not necessary for solving the problem. Exactly. Okay, and what else? The length. Then we can compute the mass according to the equation, the formula given above. Then we can find the mass moment of inertia of our subsystem. And then we might have to consider Steiner share. We need the distance from the axis of rotation to the main axis. And then we can compute the mass moment of inertia with respect to the current axis of rotation. We have 4 subsystems. Subsystem number 3, our drill hole has to be multiplied by 4, since we have 4 drill holes. The first 3 variables, inner radius, outer radius, and length, are stated in the figure given. So we simply have to find the correct value, and then the next values can be computed from them. And then we can build the sum, but of course only of the values of interest. Mass and mass moment of inertia. Okay, for the first subsystem, we can solve, or we can fill the table together. So the first one is our inner wheel, the small hollow cylinder, area 1, and the outer radius. I will use colors for you to follow my explanations, and then I will erase the colors because otherwise it will be too full. So the outer radius is this distance right here. That's the radius, given as the diameter, okay, in millimeter. It's a technical drawing. The dimensions are given in millimeter. We convert it to meter, and we compute the radius. So it's 0.075. Okay.
Excuse me, Professor. Can you please clarify which dimension does it correspond to on the drawing you have made?
Here, this outer radius of area 1.
Thank you, Professor.
Mm-hmm. Okay, now I erase that. Now for the inner radius. The inner radius is this distance right here. The diameter is given in millimeter, meaning that we have to divide by 2 and convert to meter. Then it's 0.03. And then the length is only stated in the figure above. It cannot be seen in my hand drawing. The length is this distance, 150 millimeter. it's 0.15. Now, when we compute the mass, we have to convert the density from kilogram per cubic decimeters to meter. So it's 7,200 kilogram per cubic meter. And then we can compute the mass, which is 16 kilogram. And then we compute the mass moment of inertia, which is 0.052. The subsystem, number one, rotates about its main axis, meaning that we do not have to consider Steiner shear. And then this is 0.052.
So, Professor, how did we get the 0.252 again?
This one or the one before?
The one before?
I used this equation right here. 1/2 times 16 is 8. And then the radius as stated in the equation. So 0.075 square plus 0.03 square times 16 divided by 2.
Does the other one differ from this one?
This one?
Yes, does it differ from the first one?
No, in this specific situation not, since it's computed by E square times mass, and the second part is 0 in this case. It only differs for the drill holes. Just a second. So the density is times pi times I used this equation. I just computed. I obtained 16.03 kilogram. If you use this for the density, the length is 0.15, and the radius, as stated. So obtained by calculator. This equation. Okay. And then the same for the mass moment of inertia. Instead of minus, it's a plus. And then 16/2. Okay, try to fill the table for the subsystems 2, 3, and 4, according to the figure given. I can open the breakout sessions if you like. You can join them and solve in groups, or you just try to solve it on your own for a little bit less than 15 minutes, such that we have time to discuss the solution. Okay, so try to solve the rest of the system of the problem. Okay, this is the solution of the problem. We have a absolute mass of 150.6 kilogram and a mass moment of inertia of 8.395 kilogram times square meter. I'll just give you some time to compare with your solution. And of course, if you have any questions, you can ask or write them in the chat.
We are taking whole as negative, right? Whole as
Yes, yes, it's negative. So we have to subtract from the rest. This one, this is the formula for the mass. Density times volume. Then we also had to compute the radius of gyration, which is 0.236 square root of JD over M. And we had to compute the share of the annulus on mass and mass moment of inertia. So we simply compare mass and mass moment of inertia of our subsystem number 4 to the complete total mass and total mass moment of inertia. It's 71% in case of the mass and 90% in case of the mass moment of inertia. And from this, you can also see that the effect of the mass moment of inertia, or the mass moment of inertia itself, increases the further the distance from the axis of rotation is. So the further away the mass, the object, from the axis of rotation, the higher the mass moment of inertia. Okay, any questions? Okay, if not, then this is all we will do in chapter 5. It's chapter 5 is necessary to prepare us for the problems of chapter 6. So next week we will start with kinetics of rigid bodies, and in case of a general motion of a rigid body, we need to consider the mass moment of inertia of the system, and that's why we need to be able to compute the mass moment of inertia, or at least to derive it from the formula, from the table given in the formulary. But of course, this means we will need the mass moment of inertia in the weeks that will follow. So it's not, don't forget everything we learned this week. It's necessary for the next chapter. Okay, and any questions? Yes, no.
Yes. Yes. Professor, could you please repeat what do these percentages signify? The 71% and 90%?
That's the share of the mass M4, the annulus, the outer wheel, on the entire mass of the system. And same for the mass moment of inertia. So our, due to the size of this outer wheel, subsystem number 4, and the length of 120 millimeter, the amount or the share on the entire mass is significant. So it's 71%, because our second subsystem is thin with only 40 millimeter. And then the mass, of course, is much smaller there. And same for the mass moment of inertia. the effect that subsystem 4 has on the mass moment of inertia, where is it here, is 90% of the entire mass moment of inertia, since the distance is furthest from our axis of rotation.
Yes. Okay. Understood.
Okay.
Thank you.
Okay. Yep. You're welcome.
Professor, excuse me, when will we multiply 4 in the case of third subsystem?
Because there are 4 drill holes. And here, 4 of them. 1, 2, 3, and 4. That's why we had to multiply by 4. So we subtract 4 drill holes from the system. Okay.
Professor.
Yes.
Please, for the third part where we got E as 0.15. Can you show me how you got that? I didn't get that part. I know it's we used Pythagoras theorem just as we did the other time. To get
here the radius.
Yeah. So I
this
don't
is
really
the
get
radius.
right.
This is the distance E, right? The drill hole. And so this is the center of the drill hole. And this would be the radius, the distance E. And given is the diameter, 300 millimeters. So we have to convert from millimeter to meter, and you have to divide by 2 to obtain the radius from the diameter.
Okay, thank you.
So this is 300, and half of it would be 150 millimeter.
No,
Okay.
I seem to keep getting 3.3 as the mass of our cutout. I see you've got 13.
Here, well, I multiplied by 4. So this is
okay, gotcha.
minus 4 times 3.25 is what you have probably. Yep. Okay.
Yeah, that was it. Thank you.
Okay, perfect. Well, if there are no further questions, I would stop here, and we continue on Monday with chapter 6, which will be a long chapter with a lot of practice and a lot of problems that we will solve, of course. Then have a good weekend, and see you on Monday. Bye.
Thank you, Professor.
Take care.